क्लॉज दे.
हाँ सर.
Hello, good morning. Am I audible?
Yes, sir. Yes, sir. You are audible, sir.
Okay.
Sir, this is Ravi Shankar. Good morning, sir.
Ravi Shankar, good morning.
Sir. Good morning, sir.
Yeah.
Just another some 5 minutes, sir. All are joining.
Okay, fine, no issue.
Sir.
Ravi Shankar, you see, I'm just trying to see where I can share my material. One share button is there that is blocked for me.
Sir, we will give it, sir.
Okay, no problem.
Once we start,
Yeah.
just 2 minutes, host will introduce.
No issue.
After that, actually, we will connect you, sir.
Okay, okay, great. Thank you.
Natarajan sir, we are starting, sir, now.
Good morning, Dr. Ravi Shankar.
Good morning, sir. Now I will start the session. Good morning to all. I am Anupama Hongal from EC Department, Sambhram Institute of Technology. Good morning, sir.
Morning.
So around 60 members have joined in YouTube live stream. Around 170 members are joined here. So now I will start the session. Good morning to all. I am Anupama Hongal from EC Department, Sambhram Institute of Technology. I welcome you all for the 3 days orientation program on aerospace and defense conducted by Center of Excellence, VTU, in collaboration with Sambhram Institute of Technology. Workshops are a great way for our students to gain hands-on experience and rapidly acquire knowledge in advanced research topics where curriculum-based education is yet to be developed. Workshop practice is the backbone of the real industrial environment, which helps to develop and enhance relevant technical skills required by the students. It is also of prime importance when you want to gather practical knowledge. It provides students with scientific understanding, technical competence, and provides skills to work on unique projects. Aerospace and defense industry in India is one of the fastest growing markets in the world. Cated Center of Excellence in Aerospace and Defense, VTU, along with Sambhram Institute of Technology, organizing 3 days orientation program on overview in aerospace domain with special focus on design, development, and life cycle of aircraft. Now I would like to call Dr. Ravi Shankar CV, Professor and Head, ECE Department, Sambhram Institute of Technology.
Good morning to all the participants of today's orientation program from Sambhram Institute of Technology, 6th semester students from Electronics and Communication Engineering, Information Science and Engineering, Computer Science and Engineering, and Mechanical Engineering. I am very happy to invite all of you for this program, orientation program of 3 days in association with Center of Excellence, Aerospace and Defense, which is situated at Annapurneshwari Nagar, VTU, Nagarbavi. And I am very happy to inform all of you that since from 4 years, we are in association with Center of Excellence and we are conducted many programs. And I am happy that the chairman of Center of Excellence, Commodore C.D. Balaji sir, he is also live now. But thank you very much, sir, Chairman, sir, for your kind consideration of Sambhram Institute of Technology for all your orientation program and other activities. In this platform, I am very much thankful to you, sir. Thank you very much, sir. And next, actually, I have to tell my thanks to CEA, Sri Nataraj, sir, of Center of Excellence. He is solidly behind us for all these programs. They are communicating to us for conducting such activities for the benefit of our students. Nataraj sir, in this occasion, I have to say thanks to you for considering our Sambhram Institute of Technology in all these days for your programs. Thank you very much, sir. And many resource persons in Center of Excellence are there. They are very seniors. They are having large experience in aerospace and defense domain. And one person I have to mention, he is now for this orientation program also resource person, Dr. K. Badri Narayana sir. Your solid support for Sambhram Institute of Technology and students. Thank you very much, sir, for your kind support and for today's program as a resource person.
Thank you.
On behalf of Sambhram Institute of Technology, I welcome you, sir, and thank you very much, sir.
Thank you.
And see, these programs are very much helpful for the especially engineering students of all the streams and domains. And we are very happy that this is supported by VTU and Government of Karnataka, Dassault Systems and all. And it is in Bangalore only. But as far as my knowledge and as well as COE is also accept, from Karnataka, we have to take benefit of the Center of Excellence, which is in VTU. Many colleges, many students are still not take the benefit of this, but colleges and students of other states are taking lot of benefit of this much training. And the future is aerospace and defense domain. Dear students, irrespective of you are from mechanical engineering, IS or CS or electronics, there is lot of scope and career prospects is there in aerospace and defense. All these things you will come to know in this 3 days orientation program. And I am very happy that your senior students of all these branches in the previous years, they have also undergone this orientation program and training program. And in this occasion, I will tell you, this is one of the best career area you can create yourself. And especially what I am telling is, in the present days, after processing industry or whatever industry, the growth, if you take it a 10-year growth, so in this course, if you do and if you join to this area, within 5 years, you will achieve the same 10-year growth in other areas and industries. So a lot of opportunities are there. I want you people to utilize this because they are conducting, Center of Excellence, they are conducting this one is very free of cost. And later other programs are there, training programs are there, and internship programs are there. They are very less fees actually they are offering, and nowhere you will get this much of less fees. If you go for other advanced trainings and all in other institutions or training centers, definitely it is a cost like lakhs of rupees. They are offering very cheap for you people. So I hope all the students, and they are not only conducting for Sambhram, they are already conducting these programs for top engineering colleges or like our colleges also. We have to take benefit. So end of the day, lot of opportunities and scopes are there. Very senior resource people are there. They are having, they have invested crores of rupees on software and hardware facilities, and but definitely this will help you to change your mind to go towards aerospace and defense. Again, I will tell you, all types of engineering field students can enter into this aerospace and defense domain. I hope this made you to this 3 days orientation program, made you to think in a different aspect and showing interest in aerospace and defense. After this program, you can attend various training programs, certificate programs in Center of Excellence. Definitely, you can create your future and career neatly. And coming to this orientation program, I have to say one thing very seriously for all the students and participants who are actually logging in WebEx as well as login through YouTube. So this is very serious training program. It is not a joke. Every senior people and Center of Excellence, they are spending lot of their 3 days complete time for you people only. So attendance is very much compulsory. See, almost 250 students are registered. So around 210 or 20 are already today they are logging. So whole day session, what and all training program timings are there. This is timing 10 to 1 at morning with a break of 15 minutes, and then again 2 to 5 with a break of 15 minutes. Complete day schedule is there. We have completely cancelled all your sixth semester online classes for these 3 days. So attendance is very much compulsory. Who and all just log in and log out. Everything we are having complete data. So we will get all the data with us, and based on that login and logout and whole day sessions, your presence, based on that, the certificate will be issued and you will consider for this program. If you are irregular today, their who and all is not reported, tomorrow they will not be allowed. They will not be considered. See, we are very serious to transfer important knowledge and facilities to you people. So you should also be very serious about this. And when the session is going on, I hope actually you are all learned people, you are all engineering students. You will not disturb, you will not do mischievous things. Your main intention is to listen to the resource people. And here it contains many mechanical things are there, computer things are there, electronic things are there. Don't think it is not my area, it is not my area. One single aeroplane contains all sorts of mechanical too, the electronics engineering, civil engineering, everything will be there in that. So whatever actually topics will be discussed here, everything is for you people. I hope these 3 days you will enjoy these sessions, you will learn a lot of information and you will gain good knowledge. I hope so. And once again, I have to thank on behalf of Sambhram Institute of Technology and personally myself, a big thanks to Center of Excellence Aerospace Defense, its chairman and CEA and resource persons and training people. A big thanks to you people for considering Sambhram Institute of Technology students to gain the knowledge in this area. Thank you very much, Anupama Hongar. Thank you very much. And after this, actually, you have to transfer the co-host to the IT person of Center of Excellence. He will coordinate the program. Thank you very much, sirs. Thank you very much, participants.
Thank you.
Just two words I'll say, Dr. Badri. First and foremost, it's very nice to see you again, Professor Ravi Shankar, and it's really great that we are able to do this during the pandemic. We, as you rightly brought out, we are pretty serious, and we will try to answer all the questions that the students may have. And what we also look for is something kind of a live interactive kind of a thing also, where students can clarify their doubts, and probably Dr. Badri during his course of the thing, he'll also give a snapshot of what courses they can do and what benefits that will accrue. But having said that, again, it's nice to be back with Sambhram, and so we will stand behind you, and all the very best. And over to Dr. Badri now. Thank you.
Thank you, sir.
Thank you, Balaji sir and Ravi Shankar, Dr. Ravi Shankar CV sir, for your motivational words to students. Now, I would like to introduce today's keynote speaker, Dr. K. Badari Narayana. Kanteti Badari Narayana, Principal Consultant, KTech COE, Aerospace and Defense, ETU Regional Office, Nagarabhavi, Bengaluru. He has over 38 years of experience in the field of structural mechanics, CAE, FEA, and their applications in aerospace structural components. Currently, he has been working as a senior consultant at KTech COE Aerospace and Defense, DTU Regional Office, Nagarabhavi. His specialties are area of expertise include structural mechanics, chassis and fracture, composite, FEM, smart materials, optimization, 3D painting, renewable energy system and project and technology management. His educational qualifications are MBA Karnataka State Open University, Mysuru in the year of 2011. Has completed PhD Static and Fracture, Indian Institute of Science, Bengaluru in the year of 1990. ME Machine Design, Indian Institute of Science, Bengaluru in the year of 1983. BSc Engineering, Honor in Mechanical Engineering, REC, Calicut, Kerala in the year of 1979. His awards, honors and other professional information are Innovation of the Year, Goodrich Aerospace Service Private Limited, Bengaluru in India. NDT Award from National Governing Council of NDT, Chennai. Professor Emeritus, RIT, Bengaluru. J.N. Tata Fellowship, Institute of Science, Bengaluru. He obtained several academic awards and honors, including a gold medal in recognition of his PhD work in Indian Institute of Science, and so on. He has several life member of professional bodies, in that Aeronautical Society of India, Indian Society for Advancement in Material and Processes, Structural Integrity Society of India, Indian Society for Non-Destructive Evaluation, Acoustic Emission and Society of India, Indian Society for Smart Sensor Sector. I welcome you, sir, for today's workshop. Before going to start the session, the instruction to be followed by all the participants. First, I will give you the instruction, then we'll start the session. So, attendance is compulsory for all the 3 days. Students, attendance is compulsory for all the 3 days. And if you attend all the sessions, then only you will get the certificate. For all the sessions, we will monitor the attendance. If you miss single session also, you will not get the certificate. Every day, the first session will start at 10 o'clock, and you should log in before 10 minutes. Okay, and at 11 o'clock, you'll be having tea break. 15 minutes, you'll be having tea break, and again, you should rejoin back. At 1 to 2 o'clock, you'll be having lunch break. Again, you should re-log in 2 o'clock, and you should rejoin within 1:50 p.m. I request all the participants to make the best use of it. Now, I would like to hand over the session to Dr. K. Badari Narayana, sir. Thank you.
Okay, thank you, Anupama. I require the sharing my
Thank you, sir.
presentation. Yeah, before
Okay.
actually I get the license, probably I will try to say a few words. Okay, good morning to all of you, the
Yes, sir.
faculty, Professor Ravi Shankar, faculty and the students of Sambhram Institute of Technology. And I welcome you all for this orientation program. We'll try to make it very interactive, and also you can discuss during the session. Probably the number is very large. In case more people are coming at a time, it's going to be confusing. Probably I request Anupama or somebody else to take the questions when and it's
Yes, sir.
coming. And in between, you can stop me or any other faculty who is going to take next 2 days, and we can discuss, or otherwise at the end of
Yes,
session
sir.
is also okay with us. Okay, so we are from, as you know, KTech Center of Excellence, Aerospace and Defense. Thank the management and the faculty of Sambhram Institute of Technology for giving and sharing our experience. We are hopeful that whatever the next 3 day sessions we are conducting will be definitely benefit you and your knowledge gain in this. As a part of, madam, I'm not, now it is there. I will just open my first slide so that I will start working on it. Just give me a minute.
Okay, sir.
So I hope everybody see this.
It's yet to come up. It's saying starting to share content.
Sir, go to share content.
Dr. Badri, it's not coming up yet. It's still showing, starting to share content.
I lost the connection while I'm trying to present my material. Are you able to hear me?
Yes, sir. Yes, sir. But your screen is
Okay.
not visible, sir.
Yeah, because I didn't get the sharing. I cannot share my content as of now. I'm trying to look for that.
Oh, okay, sir.
Nataraj, can you help me out? I'm at the share content, but that is not helping me out.
Mandar, do you have this with you?
That particular, what I call the button is blocked for me, share.
Badri sir,
Yeah.
the share button is there, sir. Next to start.
Yeah, I could see that the after video start share button is there, that is blocked.
Okay.
I think you have to, what you call, unlock it, or somebody has to do that for me.
Anupama madam.
Now you can share, sir.
Badri sir, now check it, sir.
So now you can share, sir.
Sir, you can share, sir.
Okay. Okay, right. I could see that.
Sir. Okay.
Are you able to see this?
No, sir.
Yes,
sir.
yeah, it's now come up now.
Okay, sir. Yeah, sir.
Okay.
It is coming now.
Okay, right. Thank you.
Okay, sir. Okay, sir.
Okay, sorry for the delay. So again, students, what I'm trying to talk is, as per our agenda, I'll try to give you very short presentation on our center. Before actually I will take you through my session on the theoretical knowledge of aerospace vehicle design. So in next 3 days, you have both a theoretical session as well as lab demonstration on the CAE tools available on 3D Experience platform. Okay. So as I requested you, I request you to give all your questions to Anupama or any other representative, or you can ask me at the end of the session. That should be fine. So going to this slide is trying to give you a glimpses of what exactly we are doing from KTech Center of Excellence Aerospace Defense. As you can see that this is an initiative from Government of Karnataka along with Visvesvaraya Technological University in association with the DS. Okay, that is Dassault Systems. We are responsible for providing us the 3D experience platform. As stated below, the objectives are nothing but strengthening the aerospace and defense ecosystem in India, in particular Karnataka, through innovation and scaling. In this next slide, you can see the team who are looking after the center's activity. As you heard, the Commodore Balaji already. So his picture is located on the top leftmost. And we have the 3 subject matter experts in the area of structure. This is myself. And we have various systems within the aircraft or any air vehicle. So Mr. Ramesh Kumar. Then we have Mr. Prasad. So he will look after the electrical and the avionic systems. And here you have the lab experts who have been well trained. They have been from the industry and trained by Dassault Systems in order to take care of various aspects of the Dassault system platforms, various modules, CAD, all CAE and other modules. And here you can see our the management staff, including IT personnel. So as you earlier seen, Dr. Balaji, Commodore Balaji is a distinguished scientist from ADA. He is the current chairman. He is former program director of ADA and a project director for naval version of LCA. And he has around 24 years of experience in the aerospace domain, most of which is in almost in the Navy. And 11 years at ADA, he is instrumental in developing the naval version of that. And we three experts on the top, what you have seen, myself, I will look after aerodynamics and aerostructures. So that is my subject, this one. A large part of my services, I was with ISRO and United Technologies. For a shorter time, I also worked with various academic institutions. Whereas Ramesh, sir, he was subject matter of experts in mechanical systems area. He has over 44 years experience, both with NIL, HAL and ADA. And he has been consultant to Jet Airways for more than 12 years in the maintenance side. And Mr. Sudarshan Prasad, he is a subject matter of expert in the area of avionics and electrical systems. Again, he worked with HAL and with ADA over 40 years, and he was instrumental in developing all the electrical and avionics systems for LCA. Okay. So in this, what you try to see is the development cycle used for design of any component, including aerospace vehicle. What you see on the left-hand side, so this one is the development cycle used for an aircraft. Okay, this includes the requirement, what I call understanding all the requirements of any product, then develop the concept, and the initial design to simulation to detailed design to manufacture and assembly, and go through the tests before actually you what I call understand the complete satisfying the requirements and release for the product into service. So the similar cycle, of course, is a very complex cycle. And here in the complete design cycle, we'll try to impart the design knowledge and also the tools. Various tools are used as you go through that. It is one way one can try to use different tools at different stages, or you can use a platform like 3D Experience, whatever we are going to talk in the next 3 days. So which has various tools within that or modules within that, you will be able to go through the complete design cycle. That is what the process we are going to take you through. So here in this slide, you are going to see the various courses, what we are covering in the center. Apart from the orientation course, what you are likely to go through next 3 days. So we have a series of certification courses are available. So what we call the internship program, or this is for the students currently in the system, or still you are doing your degree course. And after the graduation, still you would like to come to aerospace fold. So that is useful for them. That is what we call the foundation course. So in this, you have 160 hours of training given, okay, with the 30 hours of theory, 100 hours of practice. I'll have a specific slide on that. I will try to give you a little more details on that. And this course, either internship or foundation course, forms a what I call basis for going for advanced course. In the advanced course also, you will be hearing, understanding little more deeper sense, both the theoretical aspects and also how deep you can learn the tool, particularly all the CAE and other tools, and try to apply to a project. That's what actually you are going through. In this, though it is a 4 months, more than 2 months of work, you will be working on a project so that the knowledge what you have gained, the tools experience what you are trying to use, so you will perfect yourself before actually you try to look for any alternative job or probably any studies, etc. So that's how the advanced course is going to help you. And the students also come and join us at the 8th semester for your project. So that means at the end of the 7th semester, you have a semester gap wherein we'll try to, those people who have not gone through this internship program, they will go through some complete idea about aerospace. I think it has gone again. Are you able to see the presentation? I think again, the sharing is blocked. Are you able to hear me, Anupama?
Yes, sir. Huh, sir.
Are-
Yes, sir. But your screen is not visible now.
Yeah, that's what I'm telling you. My screen, what you
Sir,
call
once again you share, sir.
Can you help me getting that icon? Yeah, now I got it.
Yes, sir.
Yeah. I'm not sure why it is jumping. Okay,
Okay,
so
sir. Now it is visible, sir.
yeah, so now the 8th semester, so you can have this similar to the same course we'll try to give you, then followed by, if you bring any project, we'll try to support you to complete the project, or otherwise we can also define the project you can do along with us. So apart from that, you have value stream courses. These are all meant for industry professionals, so to upgrade their skills. Also, these are all based on 2 to 3 weeks. In the semester vacation, if you think that this is the right time, I want to develop something on the CAD, something on the finite element, or something related to electrical, what you call wiring, design to manufacturing. So we have courses lined up, around 7 to 8 courses. Anybody is interested, they can also take this certification course. So then apart from that, currently we are also engaging with certain engineering colleges. So it is not meant for aerospace, though we are talking about aerospace, what you call knowledge and the tool based and all those things. So this is useful for all the engineering graduate. So we'll try to give every semester a special elective like, so that over 5 semesters you will be hearing whatever you are trying to go through as an internship or advanced course, you will be learning third, fourth, fifth, sixth, seventh semester, so that your understanding is much higher compared to these two courses. So you will be doing in every semester some mini project as a part of this. Currently, we are working with two autonomous institutions. So they are encouraging any student from any branch can opt for these courses. And these courses, as I said, this can be what I call customized the needs of the institution and also the student interest. So what is that you are going to learn with all these courses, whatever the lined up? So you will be understanding of the structural engineering, whether it is metals or composite or any other thing. So how exactly those things are, they're going to behave and they're going to be molded into that form. All those things are coming through structural engineering. And because you have a number of systems are going to be there, the wiring, the cabling and the pipelines, all those things have to be done. That is what actually you're going to learn through equipment installation. So the manufacturing process is very, very important. So is the basic turning from what I call raw material to final product, how you arrange all the assembly of all those things, and check the simulation aspect of ergo aspects also, to make sure your operator is comfortable. How exactly we go through during the assembly, during the manufacturing, all those things are covered here. Then a number of systems are available within the aero vehicle or any other system, for example. So we'll only talk about aero system, different systems. So you will be hearing important systems, then how they perform, what all different components of that, each one, how exactly they work. Then another important thing is as a CAE tool, you need to understand simulation because we are all the time talking about virtual testing. So we want to what you call remove or actually reduce the testing, physical testing of materials to components to subsystems, so like that. So the simulation is a very important. Simulation along with optimization will try to what you call optimize the material, at the same time reduce the cost, and also at the same time, okay, safety is a very important. In order going through all this, your tools are very important. Jigs, fixtures, other tools. So you will be also hearing about the tool design. So our courses are in what you call connecting with all these different topics. So now coming to the internship course or the foundation course. These are the various subjects you are trying to go through in 30 hours. So along with that, you will also be learning about various CAD tools. So maybe CAD, CAM, then you have FEA tools, and also you have to do some sheet metal work or piping or tubing, composite design, analysis, and manufacturing. So all these tools are available in 3D experience. That's what the next 3 days you're going to have a demonstration of all the tools, how exactly they can be used. So that lab portion is around 30 hours, 100 hours, 30 hours of you have a mini project you will be doing, so that whatever the knowledge you have gained, whatever the tool skills you have gained, you will try to put that one into more than one tool you will be using in order to do this exercise. And this is about the advanced course. As I said, you have theory and also digital lab. Apart from that, you also have something related to the experts coming from the industry. We'll try to cover certain area of theory, but beyond currently what is happening in the field. So some experts will come and they'll give you. Other than that, you have a simulation experience. At the same time, you also visit to various industries and R&D labs so that you can virtually see how the manufacturing, how the design aspects are going on within that industry. So this is what the exposure you are going to get through the advanced course. And these are the various tools available on 3D Experience platform connected with the design, analysis, modeling, simulation, etc. So in this you have CATIA, most of you might have heard about it. Connected with the CATIA, a FE package, Similia and Abacus is available. So you have Dymola, then you have Delmia. So, and also you have one more, that is so as a management tool, you try to gather all the information and make sure at every stage of the component design progression. So are you satisfying all the requirement what you have stated there? That is the Innovia package. So this is what actually much more is available in this one, but this is what actually fundamental, very important for any component design. That is what the walkthrough you are going to go through. And coming to value stream courses, as I said, you have a 2-week core number of courses for 2 weeks, and you have also 3-week courses. So any of you are interested anytime, any of these courses, so you are welcome to take and get the certification for that. And in nutshell or in summary, so this Center of Excellence Aerospace Defense will provide ecosystem for R&D activity, prototyping, design, analysis, simulation, and manufacturing. All the tools are available. You can get the exposure. And these courses are, okay, whatever we have customized, this is what actually we have at this point. But the institution comes out with a particular syllabi. So definitely we'll try to support you on that also. So another important thing of the center is nothing but the students can exploit the center facilities and the knowledge base available at any point of time. You are a part of our center and get one certification, you get the badge. Using the badge anytime you can contact us and get some information you want and clarify certain things you want, and you have an idea whether the idea works or not, you want to use the tool for few days or hours, so you can always come and use it. That is not a problem, provided the tools are available at that point of time. So quickly give you the program, how we are placed next 3 days. After this one, probably I will take you through the airframe. Okay, the next 2 days on the theoretical side, we have our two colleagues are going to come talk about the electrical avionic systems and the mechanical system. In the afternoon, we have all the demonstration lined up on the 3D experience connected with the CAD, CAM, FEA, then electrical wiring routing to your model-based systems engineering. So definitely you are going to have a good exposure, and you can decide how exactly you try to take, what course is interesting to you and what course you want to practice. So all this time when we are talking about internship and foundation course, this is the course we have at this point, but we are also designed a number of other courses interesting to other students. Okay, not necessarily aerospace. As Professor Ravishankar said, this is not meant for aerospace student. Any student is required into aerospace domain because this domain comprises of multiple fields. So one student cannot try to take care of everything. So to cater for all that, so we have other courses on the composite, so design to manufacture, and also electrical harness, again design to manufacture. Then model-based system engineering is a widely used tool currently by most of the academic institutions. Thereby your design process is very clean. So people, you can take simple examples. How do you apply these concepts? You can try to do that. And the CAD and CAM integration using 3D experience. So that means wide variety of CAM processes, that means manufacturing processes, whatever is available. Those who are interested in going to the production areas, this is going to help you a lot. Of course, you need to understand how to read the, what you call, your drawings. So CAD is very, very important. From there, how to move into various aspects of the CAM, that is what we lined up. And also simulation-based design. So as I said, you do the design and you have to verify your designs. So how do you verify? So that you can cut down the cost of testing as much as possible. That is using various computational tools. So we have Similia, you have Abacus, you can do structural analysis, you can do thermal analysis, you can do CFD, you can do electromagnetic. So many things can be learned through this. Okay, at this point of time, we are concentrating on structure. That doesn't mean other people cannot. Definitely, we'll try to attempt to help you out. In all this, so you have a flavor of aerospace engineering, what is happening. So we don't want to miss that boat. Then apart from that, related to composite, whatever is required theory, we'll try to help you. And also design and manufacturing of wiring, whatever is required. So you have a theoretical component on the what you call digital lab side, and you have a huge number of hours scattered for understanding that particular tool, and also a huge number of hours help you to do your mini project. Thereby you have a gain or a strength on the tool you are going. Overall, you are going to see that you are going to work around 22 to 24 days in a week, in a month, and around 160 hours. If you want to take little more time, yes, you are always can take, that's not a problem. Generally, it takes around 160 hours. Okay, apart from that, we are also lined up understanding of the same subject for faculty, because faculty, whichever branch they are located, because nowadays a lot more opportunities in everywhere. So because aerospace field is trying to integrate various fields together, so in one go you try to understand the whole aspects of systems, then controls, then fluidic, then propellants, then so many other systems. So thereby, so the faculty going through this particular course is important, irrespective of whatever branch they are. So we have also faculty development program which runs for 5 days. So they will have a theoretical aspects, whatever 30 hours I said, that will be going on over the 5 days. We'll try to give. At the same time, we'll also try to take you a complete understanding of 3D experience platform, how these tools are trying to help you in the design. So these are the things actually at the center is catering for. So at this stage, probably I'll stop. If anybody has any clarifications, either myself or my team can clarify. So now slowly I'll go to my next presentation, that is on the airframe systems of aircraft. And also, if you want, you can reach us anytime. So this is the email. These are the other social platforms. You can always reach us. Any questions, please, before I go to the next presentation?
There is a question by one of the students.
Yes, sir.
This is, can we gain some knowledge or experience in computer hardware products with pins and wire components? Okay. I'll just try to briefly answer, and I think part of it will be covered tomorrow by Mr. Prasad. Like Professor Ravi Shankar brought out, aerospace is a domain which encompasses all fields of engineering. And there are a multiple number of computers. For example, in Tejas, which I was part of, there's at least about 30 to 35 computers of different types available on this. The hardware design is done by the electronics people, and we have the computer hardware that is available. And then each of these will require extensive amount of software that has to be built into this thing. And so software development, both algorithm level, the actual coding, as well as software quality testing is done within the aerospace community by, say, computer science people or information science people. So there is a significant amount of exposure that and utilization that computer science people have within the aerospace domain. And we have, like I said, every branch of engineering comes together. In fact, for structures, in fact, civil engineers actually do the structural design and so on. And so there is a scope, and part of it will be probably answered by Mr. Prasad in tomorrow morning session. I hope I have answered that question on one of the students there. Thank you.
So this presentation is visible to everybody, I suppose.
Dr. Bal.
Yeah. Am I audible?
Yes, sir.
Okay, how about this presentation? Visible?
Yeah, visible, sir.
Okay, right. Thank you. Okay, so quickly, next 2 hours, I will take you through the what you call airframe systems. It is one of the important system in the entire aerospace vehicle design. So in the airframe, when you are talking about the frame, you are talking about a structure. That means some shape. Okay, so the shape is given through certain materials at a certain manufacturing process you assemble together. So that's what the skeleton or the structure you are going to get it. And that is what the flying machine. And in order to fly that one, so we are talking about aircraft, naturally it flies in the air. So that means aerodynamics is the key subject which deals with how this vehicle flies in the air. While it is trying to fly, naturally, there will be a lot of disturbances. So how do you control it and stabilize it? That's what you are trying to hear through flight mechanics. In this short discussion, I'm going to take you quickly with all these things. Though I start with structures first, then take you to aerodynamics and flight mechanics before coming to materials and manufacturing. So each one of them will try to take almost a day when you come for that internship program. Otherwise, all the things are given at a glimpses. What is that you are going to understand as a part of a frame system for aerospace vehicle design. Okay, so this is a very generic one, trying to give you importance of aviation for the society. And now, as you try to see that around 1/3 population is moving around the globe using what you call by air travel. At the same time, the number of people directly involved, indirectly involved, how much is the overall turnover? And what is the growth rate? Almost around 7.5 year on year. Of course, last 2 years you just remove it. Otherwise, it is a very, very fast moving area. And now if you try to see overall aviation transport, around 35% is happening through this. And what is happening in Indian scenario? Again, this is numbers are 2 years old. And currently we are around 250 airports, out of more than 150 are commercial aircrafts. So you can see around 2.5 million people are moving around using on the air travel. And maybe equal number of tons of cargo is also moving around. And one important thing is 70% are these are made through JVs. And another important thing you try to see is what is the separation from one aircraft to aircraft when they are actually flying. In India, it is around 10 minutes. Over the next 5 years, we would like to move as close as possible to 2.5. In the Western world, that is much, much smaller than a minute. Okay, when you're talking about aerospace, we are talking about two things. One is the aeronautics, other one is the astronautics, put together aerospace, which is a very, very fascinating subject. As per aerospace is concerned, that's what actually we'll try to take you to the journey of the entire aerospace vehicle. But the only thing is that because once you are in the space, connected with the space environment also, you have to take while you do certain design. Otherwise, in this case, the vehicles are within the Earth's atmosphere, like aircraft or helicopter, etc. Whereas when you're talking about astronautics, okay, we are talking about the vehicle going beyond Earth atmosphere. That's what you have, the launch vehicles, satellite, missiles, etc. So all these vehicles, they work on three principles. So we know very well this is a balloon or airship, what we have been using centuries back. So they work on buoyancy. Okay, so we started with hot air, then we have hydrogen, then currently we are using a neutral gas helium. Okay, so then another one is using Newton's principle, second and third law. So that's where your rotating blades or helicopter or a fixed wing. So the cross section of a wing, that is what we call aerofoil. As the aircraft is moving, the air actually moves over the top and the bottom of the aerofoil or the wing. So there is a lot of changes going to happen. The velocity is keep accelerating or increasing on the top and more or less fairly constant at the bottom. This makes a big difference in the pressure differential. At the same time, the volume of air moving and the what you call momentum of the air coming out, that causes the force generated. And because this is a free body moving, so that is nothing is abstract, what you call abstracting. So naturally, it will tend to move forward because you have a reaction coming in the opposite direction. So in this particular case, you can see you have a Bernoulli's principle, you have a Newton's laws, all those things are working. Maybe I can show you a clipping about this, how exactly their principles are useful in order to make the aircraft fly. At the same time, now the third principle, what we use in the case of missiles, launch vehicles, etc. So you have the propellant that is actually ignited and the hot gases are coming out. Again, once this is airborne, so naturally it is free. So that means hot gases are coming out, momentum of the entire mass coming out is very high. So that means force is generated. That means because it is not held, so naturally the reaction force is in the other direction. So it starts moving. So that is what actually happening. So one of these principles we are trying to use in order to overcome the gravity. So and coming to the aircraft, you have lighter than the air and heavier than the air. So this is where the balloons or the airships are coming. And you have a rotary wing, helicopters, or a fixed wing. So now you have the aircraft. And as we are discussing on the aerospace design, so aerospace design looks for multiple field interaction. So this could be aerodynamics to structures to propulsion to controls to various systems and all those things. So that is why all the different fields have been integrated during the design stage itself. That is a very, very important in order to get a plane which is faster, fuel efficient, reliable, inexpensive to build and operate. And all these characteristics we would like to get through our design. At this stage, okay, for the benefit of all the students who are there, probably this clipping some of you might have seen through various media. I'm not very sure. Otherwise, this is a jumbo 747. So in a quick sense, he will try to explain to you how this big tonnage is lifted, okay, into the air. So how the aerodynamic works and which are supporting for that. And also, if you want to control, how do you control? Of course, he is not going to go into so much deeper sense, but it will definitely tell you how the what I call aeroplane actually fly.
Have ever flown on an airplane know that it's an enormous sized, amazing machine. A typical 7 can carry more than 500 passengers and weighs around 800,000 pounds when taking off. Yet it rolls down the runway at a speed of 290 kilometers per hour and, as though by magic, lifts itself into the air and can travel up to 13,000 kilometers without stopping. Incredible, isn't it? Today, we are going to learn how an airplane flies in a very simple way by going through the aerodynamics of an airplane, the main parts of an airplane, and controlling the airplane. The aerodynamics of an airplane. The 4 aerodynamics of an airplane are drag, thrust, weight, and lift. Drag, also called air resistance, refers to the forces acting opposite to the relative motion of any object moving with respect to a surrounding fluid. The energy it takes to push through the surrounding fluid creates drag. You may have noticed an excellent example of drag reduction in track cycling. The cyclist must push through the mass of air in front, but a streamlined sitting posture that cuts through the air more smoothly enables a cyclist to travel much faster with less effort. The airplane always retracts its landing gear and nose gear into the body of the plane after takeoff to reduce drag. Thrust counters drag. It is a mechanical force that keeps the airplane moving in the air. Thrust is generated by propellers, jet engines, or rockets. The compressor inside the jet engine takes the air and compresses it, and after processing from the combustion chamber and turbine, the gas is blown out through the exhaust nozzle. Here, Newton's third law of motion is applied, where the gas is pushed backward and the engine is pushed forward. Weight is the airplane body, passenger, and luggage weight in total. Lift overcomes the weight and holds the airplane in the air. Lift is created mostly by wings to keep the plane aloft. So, to keep the airplane moving, flying straight and level, this must be true, which means no net force acting upon an airplane. In any case, if drag is greater than thrust, the plane slows down. If thrust is greater than drag, the plane moves faster. If weight is greater than lift, the plane descends. If lift is greater than weight, the plane climbs. Parts of an airplane. The basic parts of an airplane are 1. Wings, 2. Horizontal stabilizer, and 3. Vertical stabilizer. The wings.
So here he is not talking about the major parts, he is talking about the parts, what is important for controlling the vehicle. We'll try to see that in a next slide.
This special shape is designed to deflect the air at the bottom of the wing due to more air strikes at the bottom and less air at the top of the wing. As the airplane rolls down the runway, higher pressure and more upward force produces below the wing and lower pressure and lesser downward force above the wing. The net result is the lifting of an airplane. Stabilizer. Stability in an airplane is a tendency to return to its initial state after a disturbance from that state. Horizontal stabilizer performs this function when the disturbance force causes the nose of an airplane to move up or down. Such movement is called pitch. Vertical stabilizer provides stability for a disturbance in yaw. Yaw is side-to-side motion of the nose, controlling the airplane. So what are the components in an airplane which control the flight, direction, and height, and maintain the equilibrium? It's elevator, rudder, and aileron. The elevator can be deflected up or down to produce a change in the downforce produced by the horizontal tail. If the elevator is deflected upward, it increases the downforce produced by the horizontal tail, causing the nose to pitch upward. If the elevator is deflected downward, then the counteracting force causes the nose to pitch down. The rudder can be deflected to either side to produce a change in the side force produced by the vertical tail. If the rudder is deflected towards the right, it creates a side force to the left, which causes the nose to yaw to the right. If the rudder is deflected towards the left, it creates a side force to the right, which causes the nose to yaw to the left. Ailerons are located on the tips of each wing. Ailerons can be used to generate a rolling motion for an aircraft. Ailerons usually work in opposition. If the right aileron is deflected upward, then left is deflected downward, and vice versa. Let's see this. To curve the flight path, the pilot deflects one wing to move up and the other wing to move down by controlling the aileron. With the left aileron in downwards direction, the lift will increase, whereas at the same time, the aileron of the right wing is in the upward position. Therefore, lift on the right wing is decreased. The result will roll the aircraft to the right. If the pilot reverses the aileron deflection, right aileron down, left up, the right wing will lift up and the airplane will roll to the left. The next time you travel in an airplane, you'll know how it works. I hope you guys enjoyed this video.
So Anupama, are we okay now or shall I continue?
Yes, sir, you can continue, sir.
Okay. So next few, somebody is telling something?
Yes, sir? No, sir, you
Okay.
can continue now.
Okay. So next few slides, I will give you glimpses of some systems and how you go through the design process. Now, if you try to take the entire aircraft design, okay, so this consists of three major systems. Okay, airframe, that's what aerostructures, what we call. Then you have various systems, both inside and outside the aircraft. Similarly, avionics. All put together, you have the total aircraft. So now I will try to take you through aerostructures. It consists of fuselage to wings to empennage, and you have a landing gear or an engine and various control systems. And this is what actually makes the entire physical body visible to us. Then within the body, you have the various systems are there, so which will provide a means of flying the aircraft. I think tomorrow you are going to hear more on this. The systems like propulsion control system, fuel system, environmental control, all those systems are used. But at the same time, you have to always navigate during the flight and communicate what you call within and outside also. At the same time, what are the parameters with which the flight is taking place? You have to display all those things. Avionics and the electrical system plays a very, very key role. So that is another system. So now you have airframe, then vehicle and avionics. So as you understand rightly, airframe is all hardware based. So that means a strongly physical integration of the airframe along with the systems. Various systems, all these systems are connected at various locations of the what you call structure. So that's why there is a physical integration of these two systems. But these systems will try to generate what you call energy and trying to transfer energy from one place to another. So wherein the systems along with avionic systems will try to communicate appropriately. So that is why there is a what you call information based connectivity between these two. At the same time, so the aviation systems are responsible to look into the completion mission aspects. That way these two systems, whatever the mission it may be, they're all information based integration are achieved. So in any product development, you might have understood all these steps are involved, critical steps, concept to fair the concept and try to identify which concept is what you call evolved to take it to the final product. That's what your definition stage. Then you go through the design at various stages of the design, and then verify your designs. Then try to build one or two components and test it and make sure everything is working as per the requirements. Then you try to release for operation. So in the operation, so a number of times various components may degrade their life. So you try to refurbish or repair them, and till you take it to the other retirement age. So if you try to say aerospace, what you call design is a very complex. So certain aircrafts will take to 5 to 6 years, some will take much more longer time. Particularly all the aircrafts what have been developed over 50, still they're working. So these are available around 80s, around 50s, around 60s, but still various variants of the same thing are working, and with the improved maybe materials, with the improved interiors, with improved capability of the engines, etc. Thereby efficiency is increased and fuel consumption or definitely emissions are reduced. So that's how in the overall design, we have to look into every aspects of that. So when you're talking about aerospace or aircraft design, we are talking about four branches connected with the airframe and mechanical systems and avionics. So this is what I'm going to take you through in the next few slides. So structures, material fabrication is trying to give you the physical, a system, what you try to see. And aerodynamics helps us the physical vehicle to fly, and this control system will try to navigate or try to support us in the movement of the vehicle from a place to another place. So this is what some of the things we are going to see. To start with, probably I will try to take you to the structures, thereby you can see the physical vehicle. Then later I will try to go through aerodynamics to control. So then in the last stage, I will take you through materials and fabrication. So aerostructures, what you try to see in the aerostructures is nothing but this is a complete aircraft. Okay, so aircraft, a number of segments are there. It is not made in one segment, so number of segments are there. And if you try to, this is the skin, and which is well covered, and so that it is a streamlined process. Thereby, the air resistance will be reduced as much as possible, or otherwise the drag is removed. If you skip the skin, so this is what actually you try to see, and that is a skeleton. If you try to understand on that every part of it, so you are going to see that these vehicle primarily you have the structure, that is the skeleton, which will actually transmit the load within various loads are going to come while it is on the ground or in the air. So in the air, you have aerodynamic loads are going to come, that it could be only air pressure smoothly or otherwise gust of air coming as you fly from one place to another. Thrust loads are going to be there. Overall weight is going to be there because it's all in dynamics. So inertial loads are going to be there. And as you go up into the atmosphere naturally, so internally you have to maintain certain atmosphere. So pressurization cycles will be there while you are taking off or landing, particularly your shock loads are there. These are all minimum what you call the design loads that are going to come. So every component of this construction has to be safe for whatever the overall design cycle is concerned, probably design life is concerned. Something like 20 to 30 years or maybe thousands, thousand and what you call 1 lakh cycles, particularly commercial aircrafts. So at the same time, it will try to protect all the interior content. Okay, it could be passengers or payloads or various systems, whatever their interior. So in a nutshell, this is how the aircraft looks like. Now you have their long body, that is the fuselage. So then you have the wings, that is what they responsible in order to generate the lift to put the aircraft in the air. And in order to control, you have a number of control surfaces are there. Main control surfaces are located at the rear. That is what we call the empennage, the tail plane. And in this, the control surfaces are identified by this black rectangles, what you try to see on the leading edge, on the trailing edge, and also here. So what you see in this picture is not only the parts and their functions, what they try to do are given in the red color. Okay, we'll try to understand more on that. So as you understand the skeleton, the major components are nothing but the skin as for the fuselage. Interior, you have number of frames are there. Okay, and all these frames are interconnected by long members, one-dimensional members. So you can call stiffeners, stringers, okay, etc. A similar construction is also there on the wings or empennage. But here the skin, then at the same time, so the number of ribs are going to be there, shorter ones and longer ones based on whatever thing. And you have a number of control surfaces are there at the rear side and the front and also in the middle. And this will also house engines, or it will also house various tankages to carry the fuel, and it will try to also support the main landing gear, or this also support the what you call nose landing gear. So this similar construction is also available here. Okay, so that is what actually happens in the wing empennage. And the engine, for example, if you try to see in all these cases also, because various systems are there, you have number of fittings and brackets are coming at various locations. These brackets are also required because the tons of wire is going across the aircraft, pipelines are going and tubings are going to hold them properly. So all those things are required. So similarly, in the case of engine also, you have a number of, the pylon is nothing but how the engine body is connected to the fuselage. That particular portion is called the pylon, the number of brackets. Nacelle is nothing but the podding or the outer covers of that one. So a number of parts connected with that, and also tail cone where the exhaust is streamlined to go out. Okay, and heat shield covering the exhaust not to come on to the what you call wing or the fuselage. That depends on where the engine is connected. And the landing gear, again, a one-dimensional or a three-dimensional members in the form of beams, axles, or struts, braces, and links. All these things are very, very sturdy and try to support the impact loads, whatever it is going to, what you call, coming during takeoff and landing. Okay, as you have seen in the clipping, so the main major forces are coming, are four of them. So that's what we call the aerodynamic forces. When you call aerodynamic forces, the lift and the drag are aerodynamic forces. This is by virtue of system weight, payload or cargo, the weight is acting down. And the aircraft as it is moving, you have the engine actually push it forward. What is the thrust required in order to overcome it and accelerate it? That's what actually we are trying to see different. So if these are the forces and also other forces, you talk about aerodynamic forces, you got the weight, you have the inertia, you have the what you call shock forces, you have the pressurization, all these forces, how they get equilibrated within the system or the skeleton, what you have seen, one-dimensional elements, there could be rings, there could be longerons, there is a skin. So how each of the member is behaving, if you try to go where the load is generated, where the load is passing, that's what we call the what you call load path. You try to understand that all the loads are disseminated in the form of these fundamental forces like tension or compression or torsion or shear or bending. This is what you'll be doing in your strength of materials or your what you call design of any mechanical elements. So same thing will happen everywhere. These are the fundamental forces. Probably something else happen at the pressure load. Finally, the pressure loads you try to synthesize and finally try to see. So you have a axle loading, you have a hoop loading. So those things are visible to us. Then you try to see how the material is actually going to behave, how these components inside are going to behave, what sort of failures they are going to see, how the failure they are going to see. And also you need to understand, but wherever the engines are there, other things, the temperature is also changing. So, and also the aircraft, helicopter are moving with the different environmental conditions. So a lot of dust it accumulate, corrosion is also going to be there. So material also get deteriorated. You need to worry about that. In all these cases, you have a dynamic loading. That means the fatigue is there. So that means the fatigue failures are also going to be important. So you have to see all possible modes of failures of your basic components and the basic material, whatever you are trying to use. Okay, so when we are talking about this construction, so finally these basic elements are arranged in the form of frames. So that's what we have been using over centuries. Or they can be used in the form of monocoque. That's where you have a thick sheet, okay, which takes the entire load, but in order to keep that in particular shape, so you have number of frames which are trying to support it. And in case this construction is assembled in what you call different segments, in order to assemble that, you have a bulkhead. It is also something like a frame, but a solid, a little bulkier than the frame. That's why we call that a bulkhead. And this construction, you can see a number of ground-based equipments even today. Okay, but when you're talking about aerospace industry, you want to improve the what you call reduce the emission levels, improve the performance, and reduce the fuel consumption as much as possible. This construction, though we started centuries back, over the years, as the technology improved, as the knowledge and the material systems are improved, manufacturing systems are improved, various systems are improved, we have come to a stage where a lot of optimization is possible in this construction. That is where we call it as a semi-monocoque, wherein the construction is very similar, but here is a very, very thin shell. Here maybe you are using few what you call MMs. Here maybe hardly 1 mm or 1.5, much lower than that. And whereas you have a number of frames and also longerons or stringers are there, these constructions are virtually used in the aerospace. Now also it is going on with the automotive. Other industries also slowly adapting to this in order to make it very efficient. At the same time, whatever life is there, we cannot compromise. Safety, we cannot compromise. You have all the things in place, at the same time reduce the weight as much as possible. Apart from that, certain components we are also going, though I have not shown any picture here, that is what we call the sandwich construction, which is a much, much lighter construction. When you are talking about all the control surfaces of the aircraft, so all the control surfaces are made of the sandwich construction most of the time. Maybe they're also stiffened, but because that is a weight important, wherever you can cut down, you can cut down. As a designer, as a structural analysis person or a structures person, you need to understand, so what is the load generated, where it is generated, what is the path it is actually transmitted. That is what actually you need to understand. When it is moving through the basic elements of the structure, okay, so whether the member can carry the load, in what form it is going to carry the load, or these members are efficiently placed in order to take care of this load distribution. And you have to talk about these members when they are going to fail. What is the maximum load carrying capacity? So these are the some of the things we'll be always thinking as a structural engineer or a design engineer. So thereby you can really address all the failure modes of your component or your construction. So this is what actually people are going to learn through the structures, any structures, it doesn't matter, not necessarily aerostructure. But aerostructures is much more stringent from quality point of view, from the regulation point of view. So vigorously we'll try to implement that. So at this point, probably I'll try to show you one more clipping, another 2 or 3 minutes clipping. This is a student project where you are going to see the skeleton of a business jet, okay, developed by MSc students, where you can try to see structural elements, every what you call major components, fuselage to wings to empennage to then landing gear, and also various mechanical systems are, you can see few of them, and you can also see some avionic systems. You can see the structure. You can understand fuselage, how is the construction. This will change from vehicle to vehicle. There is no uniqueness. It is the novelty is your innovation. How do you conceive the loads coming? How exactly you want to place your material? In what form you want to place the material? You can see a series of groups here. The horizontal and the vertical stabilizer with the number of ribs. Based on the aircraft, you can think of different construction. You can see the landing gear, entire wing. As you walk through the wing, how is the construction? In order to reduce the weight or in order to allow certain tubing and piping or maybe electrical wires to take care, you may require certain what you call cutouts. Then how do you attach the landing gear, main landing gear? Now you can see different systems. Prominently, they are going to show you the fuel system, propellant system, and also electrical system, and the tubings. And also they show you the fuel tanks, where they are located. A few avionic systems, radars, etc. So now I'll take you through another system, that is aerodynamics and controls together. Probably this 11:28, can we stop for 10 minutes and then come back?
Yes, sir.
Okay, thank you.
Now
Then,
we'll,
yeah,
yes,
11:45, we'll try to meet.
okay, sir. Okay.
Yeah.
Dear participants, the session is on only. So you can have tea break for 15 minutes. 11:45, you can come back.
Hello.
Sir, we can hear your voice, sir.
Okay, so I want share button to be
Yeah, co-host. Yeah, sir. Anupama, madam.
Sir, sir, shall we
Yeah.
start now, sir?
Yeah,
yeah,
madam.
please.
Okay, sir.
Still, I'm not able to share.
Hello, Anupama, madam.
That is blocked.
Yeah, yeah. No, 1 minute, sir.
Sir, now you can start the session, sir. You can share the screen now.
Still, I'm not getting that, madam. That is in the blocked condition only. Okay, now I got it. Thank you. Yeah, you're able to see this?
Yes, sir.
Okay, right. Thank you.
Yes, sir. Yes, sir. Now we can see, sir.
Yeah. So if any of the students have any observations or they have any doubts so far what we have covered, quickly 1 or 2 questions. Otherwise, I will proceed further. Okay, if there are no questions, probably I'll try to continue. So the next topic, what I'm going to cover is aerodynamics. As I given the information, aerodynamics, what is that we are looking is, it is a study of loads exerted by the airflow over the body. Okay, so in this particular case, we are talking about the aircraft, particularly the wing. Okay, so what sort of force it is going to generate, how it is going to support our airlifting of the body and stabilizing the body there. So this particular principle can be used with the aircraft, wind turbines, or any object that moves in the air. So how it works? So this has to generate the pressure differential based on the configuration, and also it follows the fundamentals of aerodynamic laws. So that is nothing but a conservation of mass to momentum and energy. Okay, so you might have heard about Bernoulli's principle, particularly all the people who are actually from the mechanical side or those who have taken the fluid mechanics. So that is nothing but your momentum energy, what you call equation. So that can be what you call simplified to Euler's equation, and that is trying to give you a relation between the pressure variation to your velocity. At the same time, now to that, you try to add one more term that is nothing but the potential energy of the fluid particle with respect to ground anything. So that is what actually your Bernoulli's principle. In this particular case, we are assuming the aircraft is moving parallelly with respect to the ground. So that particular term goes. So that's how actually we try to use Bernard's principle in order to understand what is the pressure variation, how this pressure variation effectively by using the contour of the what you call moving body. So particularly we are talking about the wing or a cross section of the wing that is aerofoil, contoured in such a way that you will get the best benefit out of this. And together with the energy, to go conservation energy you try to put. So this is what actually you try to use in your computational fluid dynamics in order to evaluate, okay, what all the velocities at any location in all the directions, and then pressure, temperature coefficients. So these effectively all these laws are very much important. At the same time, you have to also understand the basic parameters of the air. So that's what we are talking about, aircraft moving in the air, like pressure, temperature, density. Okay, so and how it is going to change with the altitude, probably 2 kilometers up to 10 to 12 kilometers. So naturally atmosphere is going to be changing. So the density is going to change. So accordingly, all the parameters are going to change. And at the same time, based on the speed of the vehicle, whether you are going on subsonic to transonic to hypersonic or supersonic to hypersonic, so the compressibility effects are going to come more and more faster you try to go, air will be compressed a lot. So that influence of all those things will be there on the aerodynamic parameters. So ineffective, when you are talking about the what you call speed, you are talking with respect to sonic speed. So that is where the Mach number is coming. So you have the pressure, you have the temperature, you have the density, you have the Reynolds number because the drag is coming into picture. Okay, and you have the Mach number. So all these things are trying to give you an understanding about what configuration is more appropriate for a given airflow or a configuration of the aircraft. So this is how actually aerodynamics, what you call concepts are slowly what you call become little complex, and it is not. As you try to understand step by step, I think the process is quite simple. And as you also see that most of the time the aircraft, particularly commercial aircraft, they will be in the cruise position or the level flight position. So that means what, in the level flight, the lift generated is such that it will try to take care of the weight, and the thrust by the engines you try to take care of whatever the drag generated. So this is the equilibrium condition what you are going to get. So that is what is going to happen in the straight what you call straight line or level flight, where the flight is moving at a constant speed. In other words, lift and weight are related by this, and the weight is nothing but m and g, because it is overall mass, what you call, multiplied the gravity. So that is given by aerodynamic term, that is L. The lift is given by rho v square S and CL. Important thing here is rho is nothing but the density of the air, at what velocity the object is moving, and what is the surface area where the lift is generated. Okay, you have a huge surface area is available where the lift is generated, where you have a proper aerodynamic differentiation of pressure and velocity. So that will happen only on the main wing and the tail wings. But the amount generated rest of the portion is very, very small. But they contribute a lot to what you call a drag, but not for the lift. So that's why while you try to size the aircraft, we will try to size with respect to the lift is generated by the main wings. So what is the wing area required? That is what actually going to happen here. Similarly, when you try to take this equation, because we have the thrust and the drag has to match, so that means you have the engine capacity. How do you find out the engine capacity? You have to identify a case wherein what speed you want to move, what is the total surface area. Now, the drag is coming everywhere. So you have to take every bit of the drag coming from every portion of the aircraft. That's why this area and that area is a difference. One need to understand, and that is what actually the minimum size of the what you call the aircraft engine. So that can be generated by the jet engines or that generated by propellers. So that's why you have two equations: jet engine, the efficiency; propeller, its efficiency; and also what is the maximum speed it can, critical speed it can move. So these are the equations are useful in the earlier design of your component in order to find out how much is the wing area, how much is the aircraft, what you call engine requirements. So these are what you call simple things. And if you try to see the element like lift, so here, as we said, Bernoulli's principle, or we talk about Newton's second and third law, effectively you try to use it. And this is the equation for that. And now you try to see the aerofoil, that means a cross section of the wing or the blade. Okay, so air is actually moving in the higher velocity on the top side compared to the bottom. So there is a pressure differential. At the same time, if you try to say the contour of the aerofoil is such that, so it is actually the amount of air moving, so gradually changing its direction. That means the rate of change of momentum. So that is nothing but the force generated. A component of the force is nothing but you integrate normal to the aerofoil or normal to all the aerofoils along the wing. So that is what actually resulting lift, what is that we are going to see. So in this process, how the aerofoil is what you call tilted with respect to the airflow, and what is the contour of the aerofoil, how much is the surface area of the aerofoil, what speed the vehicle is moving. So these are the number of critical parameters what is going to give you. So when you're talking about the lifting surface, so we are talking about the aerofoil or cross section of the wing. So these are all the nomenclature. I'm not going to go into details. Rather, the curvature, whatever is happening, this is what actually responsible in order to generate what you call accelerated flow here and normal flow here. That is what actually trying to give you a positive what you call pressure here, negative what you call a negative pressure here. In turn, there is a lift in that direction. Okay, so as I said, these are all the different factors that is coming: shape, size, velocity, inclination. Okay, then mass of the flow, how much it is moving. That is again depends on the speed at which it is moving. So then the Reynolds number, then you have the Mach number. So and the density of the air at that altitude. So these are all the some of the things they will try to give you. So another important thing is, okay, based on the nose up or down. So that is required in order to control. At the same time, during any disturbance is there, you try to change it. So based on that, so now what happens is a smooth flow that is going to take place. So now this leading edge and trailing edge, whatever you try to join that, that is what the card. With respect to airflow, you try to lift the nose up. That's what the card is, the angle of tilt is increased. So now you say airflow is taking and going in that direction. Now this is all what you call a higher velocity, that means a low pressure, and this flow tend to move inside. So that is what actually you have a lot of turbulence. Okay, any turbulence is nothing but a drag. So that means this is going to cause the lift to come down. So that's why important parameter what the designer look is angle of attack. That means how this angle is changing with respect to airflow and how the lift is being generated. The lift is keep on increasing. At one point, it actually that starts coming down. So beyond that, we should not operate the vehicle, particularly the initial stage where the velocity component is very small. Initially, that is on the ground about to lift. So you have to appropriately take care of by the area. But the fixed wing area is fixed. So you don't have the area is already there. So you have to generate additional area in order when the vehicle is moving at a slow speed during the initial stage. And also you try to give the curvature such a way that you try to generate more negative pressure. So how do you do that? So that is where you have a number of control systems are going to be there, flaps on the leading edge and trailing edge. So these leading edge flaps you call slats or slots. Otherwise, they are control surfaces. They will try to deploy, thereby they expand from the initial position. That means from the wing, they will try to move out, thereby wing area is going to increase. At the same time, curvature of the area. Now you try to see these flaps. So earlier they were straight, now they have gone. So that way the curvature is changing. Or earlier this is inside, now this has come. So that means there is a curvature change here. So there is a slot here. So in order to effectively give more area and also more streamlined path, as the air allowed to go through this, more streamlined path is going to come. These are some of the ways you try to improve the lift. Now you see, without all these additional surfaces, your lift is somewhere here. By having the slots on the leading edge, your lift is going to be increased for any angle of attack. By having these what you call flaps, you are further increasing it. So effectively trying to use these two surfaces so that you try to use it effectively when there is a requirement for higher lift. Okay, so now coming to another aerodynamic parameter, very, very important parameter, which involves in the sizing of the engine. So the drag. So the drag is a wasteful work. We have to cut down as much as possible, but you don't have complete control. What you have control is how to reduce the drag by various means of streamlining and perfectly maintaining the surfaces, and also interference between one body to another body where they are connected. So that's how there are various types of drags. If you are able to control all these what I call components of drag, overall you try to reduce it. So to give you a flavor, probably in the fluid mechanics, maybe mechanical people or other streams of engineering, if you have gone through, you have a plate. Okay, the stream is going through, equally go through both the sides. Pressure differential is nothing but zero there. Or if you put the what you call aerofoil like this, so that means what, there is some pressure differential. When you try to put a ball over which you try to allow, there's a huge amount of turbulence. So that means the pressure variations are very, very drastic. Okay, compared to friction, the pressure distribution is causing that. Or the same plate you try to put 90 degrees. So the virtually, so you have the form dog. The nature of the construction, the form is such that you are going to get 100% drag there. So these are the things which will try to visible to us. Based on that, you try to streamline. That is what the message is here. At the same time, so we'll try to see with the angle of attack, we also seen how the lift is increasing, how the drag is also increasing. So this will not try to give us where exactly the optimal point and how to make use of that optimal location in order to cut down the fuel cost, at the same time make the entire journey comfortable, at the same time efficient, what do you call the performance. So for that, so we try to use what is known as possibly drag what you call lift versus drag will try to form, and that's you try to identify the location where you have either L by D or coefficient of lift by coefficient of drag. So this is a large. That is the point you have to operate the what you call a machine such a way that you are going to get a very good fuel efficiency. And this curve, what is that we talk about drag polar. So that is a very, very important design at every stage of design of the aircraft. Another important thing in the aerodynamics, as we talk about what we call computational fluid dynamics. So two things, you can make a model and try to do internal tests. That is what actually testing. And maybe at every component you have to do every what you call the what you call, prototype level, small one, bigger one, like that you have to do. You have to put all the information together, and finally you can come to a conclusion how much lift, how much drag, and what is the capacity and all. So now the advent of development of the softwares and also high powerful computing systems, it is always possible to reduce or minimize the testing as much as possible, understand various variation of all the configurations, and get a best configuration for the aircraft, whatever under design. So these things are possible with computational fluid dynamics. So this slide will try to give you the summary of the overall thing. What you try to see in this slide is nothing but, as we try to see, so on the lower side you have positive pressure, on the upper side you have a negative pressure. So as you come towards this end, so now what happens is this positive pressure wants to go up, but the aircraft is moving forward. So by the time it comes, it will leave that one. So that way it is trying to leave a wake. That is what actually we call the vortices. So this is actually some form of drag again. So we want to what you call reduce as much as possible. So the reduction is possible what is known as winglets. That's what actually you try to see. A small projection at the end of that. Whatever is happening at this area, you are making it to happen much far with a small construction. So try to reduce the drag as much as possible on the main wing. So this is another technology developed by Boeing way back 70s that is also extensively used. So I will try to show you a clipping. Okay, so in this clipping, what is that you try to see is this aerofoil. So try to use the principles and how the lift is generated. So that's what, and this is generated by Cambridge University professors, and they will try to give the essentials of
Airfoil technology helps human beings to fly. Turbines.
okay, so that's how actually you are going to get the lift. Of course, along with that, we have also drag. We have to minimize the drag as much as possible. Various means we have seen how to do that. Similarly, you have to improve the lift as much as possible for various flight conditions. When we are trying to talk about various flight conditions, the atmosphere is not same. Point to point, it is going to vary. It is going to vary the density and the pressure and temperature there. So thereby, so now the lift parameters are going to change. So whereas the drag is also changing. So thereby the aircraft actually deflects. Okay, so this may be a static deflection or it can be a dynamic deflection. If it is going to be dynamic, you have to set back to the what I call a normal position. So that is where your stability and control actually comes into picture. That's what we also call it as flight mechanics. So why are you trying to do it? You have the mechanics and dynamics in order to make sure aircraft does the right, what you call work, whatever is designed for. At the same time, all these things should help the or ease the pilot so that he can have a good handling of all the flight qualities. That means the pressure, temperatures, or you are talking about any bumping, how quickly he can control and then get back to the normal condition. So in order to understand these the principles, it is very important to understand the axis of the coordinate system. And at any point, as every one of us know that there is 6 degrees of freedom. So that means any particle move on 3 axes and also rotate about the 3 axes. So that is what the aircraft, the center of the aircraft, probably the middle of the wing, in the fuselage towards the nose side. And if you try to see, there is a along the fuselage, that's what generally called longitudinal axis, and along the wings, that is called the lateral axis, and normal to these two axes, you have the vertical or normal axis. The rotation about longitudinal axis we call as roll. Similarly, pitching, what you call nose up or down, that's what actually we call the pitch rotation. Okay, turning towards right or left, that's what we call it as yaw. So this is what is important, and which are the controls which are actually trying to, okay, what you call move or rotate the vehicle in these three axes. So that is what actually primary control surfaces. So these primary control surfaces are located. So one set of surfaces are located here, ailerons they call it, is on the wings at far away from the midsection of the wing or the fuselage, and another two control surfaces are there in the empennage. So that's all the color coding you have given. So using this, you will be able to control as closely what I call static position as possible. So you have the ailerons, the elevator, and the rudder are far away from the CG point of the aircraft, so that any small change in the force distribution, that's what you have seen in the very first clipping, while you are differentially operating what I call these ailerons, it is possible when the aileron is located to, or deflected in such a way that you are going to generate more area in a what I call favorable configuration. In that side, you are going to generate more force compared to the other side. Particularly if the aileron is lifted up, so that means you are disturbing the airflow going there. So naturally, the pressure is disturbed, the force is also coming down that side. So that means one side force is more, other side force is less. So this will try to lift. At the same time, vehicle is moving forward. There is a tendency for this to rotate that direction. So this is how actually you try to use the control surfaces. Similarly, when these were this horizontal surface or the vertical surface, they work together, either move down or move up or move right or left, the rudder will try to do. So when it is moving right or left, so this will try to move right or left. Whether this is acting down, the force is developed in such a way that it goes down, nose down. When it is acting up, so the forces are generated in such a way that the nose is going to be up. So this is how we try to use the main or primary control system along with whatever the pilot he has the throttle. So he will try to use these four what you call controlling elements, and thereby he will try to get the entire machine under his control and make sure that the flight is very safe. So what you can observe is you can I request you try to see one by one at a time, so that you can feel exactly what is happening by changing the control surfaces and motion of the control surfaces to what is happening to the aircraft, how it is actually rotating. So you can see the roll rotation, a pitch rotation, or yaw rotation. Okay, so that's how the control surfaces work. And here, as we see, we have primary controls. You have the ailerons here. Then you have the horizontal stabilizer, vertical stabilizer. You have the elevator to rudder. And you have a series of flaps on the what you call rear and what you call leading edge of the aircraft, what we call the slats or slots. And also on the top surface here and here, you are going to have the spoilers. So these surfaces, what we call the secondary surfaces, are high lift devices. Particularly, they are going to be used during landing and also takeoff, because during takeoff, as you said, you are trying to fly at lower velocity and gaining the what you call velocity as you go. So naturally, you require more lift. How do you generate? By changing the contour of the wing at the contour of the aerofoil. At the same time, increase the what you call the surface curvature also you are trying to change. In turn, you are trying to get that. While you are about to touch down or land, you want to cut down the speed. So you have to apply. Air brakes can be applied, or you deploy your from flaps in such a way that it will try to resist the airflow and try to give you the speed at which you wanted to actually bring it down. So this is what actually you have a primary control surfaces and a secondary control surface. Okay, so this is again 1 minute. This one I will try to give you.
The aim of this series of lessons on flight controls describe the various primary and secondary flight controls that are available to you, the pilot, and to explain the mechanics of how the pilot's flight deck inputs cause the controls to move. Aerodynamic reasons why flight controls have the effect that they have on the aircraft is outside the scope of these lessons. We will only touch on the theory here when it is necessary for reasons of clarity. In this first introductory lesson, we will look at how an aeroplane moves around its axes. For steady flight, the aircraft must be in a state of balance, 0 moments around its axis. The primary flight controls are designed to enable this to be achieved for all possible configurations and center of gravity positions. Controls are also required to maneuver the aircraft around its 3 axes. The 3 axes about which an aeroplane rotates are the lateral axis, the longitudinal axis, and the normal axis. The movement around an axis is produced by changing the aerodynamic force on
Now
the
you try
appropriate
to see here,
airfoil.
this is the camber or the curvature what you are trying to change, and at the same time you are going to get more area.
Changing the angle of attack or incidence of the aerofoil, or decreasing the aerodynamic force by spoiling the airflow.
These are all the spoilers.
The most common method used is to change the camber of the aerofoil. This is done by deflecting a control surface on the trailing edge of the aerofoil, either up, decreasing the camber and the amount of aerodynamic force generated, or down, increasing the camber and the amount of force generated. This principle can be applied to control about each of the axes. Aircraft rolls about its longitudinal axis. The devices most commonly used to control roll are the ailerons. The ailerons are operated by rotating the control wheel or yoke, or by moving the control column or stick laterally. Rotating the control wheel clockwise will cause the left aileron to move down and the right aileron to move up. The aircraft will bank to the right. Counterclockwise rotation of the control wheel will have the opposite effect. That is, the aircraft will bank to the left. The aircraft pitches about its lateral axis. Pitch control is most commonly achieved by the use of elevators. The elevators are controlled by moving the control wheel or control column fore and aft. Pushing the control wheel forward lowers the elevator and the aircraft pitches down. Pulling back on the control wheel raises the elevator and the aircraft pitches up. Aircraft yaws about its normal axis. Controlling yaw is normally achieved by the use of a rudder. The rudder is controlled by the rudder pedals. Pushing the left pedal forward causes the rudder to move to the left, and the aircraft nose to yaw left. Pushing the right pedal forward causes the rudder to move to the right, and the aircraft nose to yaw right. The ailerons, elevators, and rudder are known as the primary flight controls.
Okay, so now we'll move on to the next topic, that is on the materials. So important thing as a designer, always we look for what you call lightweight materials, and which will try to give you higher strength and stiffness and durability. All these factors are very important. Similar thing is also true with aerospace materials. And also we have to always constantly look at the cost parameters, particularly for material purchased to actual final fabrication and then assembly side. And at the same time, you also talk about stability, reliability during the usage of the entire vehicle throughout the life cycle. Okay. So apart from that, another important thing we have to see is about the durability. So durability is nothing but how long my components or my material can work. Okay, so this has to go through without any replacement. What you call, this is what actually we expect, but that may not be true all the time. So these durability elements are in the form of fatigue. That means what, a lot of vibratory loads are going to come. Aerodynamic variations are going to come. So that means what, these vibratory loads in turn generate fatigue. That means a very, very low amplitude loads and stresses. So though they may not cause any failure immediately, they will cause over a long period of time. Okay, so those things are going to be very, very important. Then the next one is going to be a corrosion, because the aircraft is moving in various environmental conditions. The corrosion is going to be a very, very important segment in all these things. Then, as we said earlier, so in the aircraft also, there are a number of elements which are moving relative to the other element. So these elements have to be taken care very, very carefully. So otherwise, where is going to take place, and that means what, there is going to be what you call the gaps between the relative motion between the elements. So that causes problem. Then vibration, then there is a breakage will be possible. At the same time, as you know very well, there is a number of systems which are working at various temperatures. So that means what, the creep is another important issue. So we have to take care of that one. So all these parameters are going to be very important while we try to select aerospace material for any aerospace vehicle. Okay, so if you try to see, traditionally, this is what the material we have been using. So if you try to see, aluminum is going to be around 75%. The composite material, very small quantity, steel and titanium. So otherwise, these are the various materials being used, and aluminum alloys to magnesium alloy, then your beryllium alloys, then your steels and titanium alloys. So of late, composites really over last 50 years, there's a huge development in the development of materials, the what you call materials and manufacturing procedures, the machining procedures, understanding their behavior, how they fail, and how to use with usage what they're going to have, how they are going to happen. And a similar thing is true with plastics or polymers. And in some cases where high temperature barriers we want to use, ceramics are also generally used there. So in all this selection, apart from strength and stiffness, as I said, the cost is also a very important thing. So another important thing is the durability, fatigue, corrosion, toughness, wear and grip. These are all some of the points we have to keep in mind. So if you try to see the major materials over a period of time, which is being used in the composite area, in the materials area, you try to see here the um, aluminum over a period of time as the composites evolved and their developments have taken place from every aspect of the composite usage around 2010. So that is the first one is Boeing 787. Around 50% of different composite materials are being used. They have cut down the aluminum to a larger extent. So usage of aluminum, there is a competition from composite, and that is slowly coming down. So other materials, what we have is the titanium, then you have the steels and other materials. A small percentage here and there based on the aircraft, whatever we are using. So they will be keep changing, but otherwise, generally their usage is more or less maintained. Okay, so otherwise now the use of composite, so which is lightweight, so thereby we are trying to reduce the emissions at the same time. So the system, overall system is more becoming very efficient. And the coming to the different failures of the structural elements by fatigue, almost 55%. The corrosion around 16, and overloading because of the environmental conditions and in which the flight is actually taking place. You have almost close to 85% is here. If we are able to manage and control all these things along with the corrosion, and also loads are also going to be there. So that is where the stress corrosion and fittings going to be there. They will join together, form the cracks. The cracks are going to grow. There are going to be there everywhere because whatever is there outside surface, we can always see, always clean, always protect. But the interior surface, okay, were covered with a big plastic cover, but the metallic surfaces are still not visible. So we may not able to 100% make sure they are not corroding. So they are the ones which are what you call causing problems, and we need to understand that. So as we discussed already, wear is a very, very important thing. And high temperature influence, particularly the creep, the connected with the turbine or engine components are very, very important. So in this slide, okay, in a nutshell, I'm trying to give you everything as the vehicle is moving ground to air to ground. So various loads are going to be there. All those loads, small or big. So they are going to create fatigue. They are going to create fatigue, and that means there is damage. And this damage sometimes could be noticeable. You can repair it. Not noticeable, so you can see a huge, what you call problems of this nature. These damages not coming from the mechanical area alone. They may come from the corrosion side, and the material thickness is coming down, and the loads are such that they will start actually the cracks are generated and propagated finally, what you call in an operation without the knowledge, simply they rip apart like that. So the same thing is in the case of high temperature applications also, in the case of rotor discs or the blades, and over a period of time, because you have the centripetal force, that means this entire construction is under tension all the time and rotating for hours together with a high temperature. So the creep is going to happen along with the unknown sources. Actually, any fine defect is generated, and it will try to propagate, and it may come out of the casing, maybe. So these sort of accidents are all then. At the same time, you have to also worry about the wear and tear between different components which are under relative motion. Okay, so these are all the important things one need to understand while we consider the material for a particular application in the aircraft industry. Not necessarily aircraft, everywhere it is the same. But these things are very, very important. So in this clipping, probably it will take I think 4 to 5 minutes, a little longer. He will try to give you, explain every metallic material to plastic to composites to where exactly they are being used, and what sort of what you call the damages are going to be there. Particularly concentrate on the corrosion side much more, and what are the influence of the corrosion on reducing the life of the component. Corrosion, stress corrosion, what you call stress corrosion, and different types of corrosion. This is what actually giving through this clipping.
In this lesson, we will begin by looking at the materials from which aircraft structures are made, and we will look at the effects of corrosion on these materials. We will also examine the effects of a hard landing on the aircraft structure, and we will look at failure statistics and their effect on flight safety. We will finish the lesson by having a quick look at the maintenance methods employed to keep aircraft in a safe and airworthy condition. Modern aircraft are constructed mainly of aluminium and its alloys, with smaller amounts of steel and titanium for the major structural components. Composite materials are used extensively for more lightly structures. Each material is chosen for its particular properties with regard to heat strength, wear resistance, strength to weight ratio, fire resistance, and so on. Aluminium alloys are the most widely used metals for structural use, due to them having a good strength-to-weight ratio. Duralumin is an aluminium and copper-based alloy, which has poor corrosion resistance, except when clad with pure aluminium. It has good thermal and electrical conductivity, and good fatigue resistance, but it is difficult to weld. Aluminium-clad duralumin is the most popular material in use for airliner skin. Steel and its alloys are relatively heavy, but can be made very strong. They are used only where strength is vital and weight can be ignored, for instance, undercarriage units. Titanium is much lighter than steel, but it is just as strong and can be used where fire protection is required, for instance in engine firewalls. Titanium has good strength, and it retains this strength and its corrosion resistance up to temperatures of 400 degrees Celsius. It is, however, expensive to produce. The SR-71 Blackbird was the first aircraft to make extensive use of titanium within its structure, paving the way for its use in modern fighter and commercial aircraft. The Boeing 777 uses some 58 tons of titanium in its construction. Magnesium alloys are also used. Their principal advantage being weight. Magnesium alloy has an excellent strength-to-weight ratio. Aluminium, same strength, being 1.5 times heavier. Magnesium alloy has poor elastic properties, so its use in primary structures is limited. It is often used in the construction of gearboxes. Composite materials are becoming more and more used in aircraft construction. They are made up from layers of fiber, carbon, glass, Kevlar, molded into the required shape with a hot plastic resin, which is normally epoxy. Carbon fiber reinforced plastic is used where structural strength is required. It can be produced with the same strength as an aluminium alloy, but with a weight saving of about 20%. Glass fiber reinforced plastic does not have the same structural strength, but is often used for fairings and non-load-bearing panels because of its light weight. Kevlar has very low electrical conductivity and high fire resistance. Aircraft cabin doors, overhead bins, and bulkheads may be built with honeycomb pores made up of Kevlar. Composite materials have good resistance to corrosion and can be easily formed into complex shapes. But their fatigue behavior is different to that of conventional metal alloys. Metal structures suffering fatigue retain their design strength up to a critical point, after which failure occurs very rapidly, whereas composites lose their properties gradually. Interest in composites for structural use is due to their high specific strength and specific stiffness, aligned with their ability to retain these properties at high temperatures. The Airbus A380 uses a significant amount of composite material in its construction. The tailplane, for instance, is almost entirely constructed from carbon fiber reinforced plastic. Corrosion is the slow destruction of metal by electrochemical reaction. It is one of the most persistent defects found in aircraft. Rectification of advanced corrosion has been known to take thousands of man-hours. In fact, more than 10% of engineering downtime is spent in dealing with corrosion problems. It is therefore essential that it is recognized at the earliest possible stage, and that effective preventative measures are taken. When a metal is exposed to the air, oxygen in the air reacts with the bare metal to form an oxide film, which adheres to the metal surface. This oxide film forms a barrier between the air and the metal surface, which can protect the underlying metal from further attack. A good example of this is the Statue of Liberty. It is clad in copper, lit and developed a clean copper oxide coating, which protects the metal from the elements. With the exception of oxidation, all other corrosion takes place when the metal is in contact with water, either as liquid or as water vapor in the atmosphere. Corrosion is mainly electrochemical in character and occurs in conditions that permit the formation of minute electrical cells in or on the intact metal in the presence of an electrolyte. It will also occur when a difference in potential exists between the entire surface of the metal, or it may penetrate locally, forming deep pits, or even follow grain boundaries inside the core of the metal. The weakening effect can be aggravated by stresses in the metal due to external loads, or there may be residual stresses from the manufacturing process or method of assembling.
So, yeah, so he will continue.